Hello everyone. Unfortunately, the recording failed, so I will have to redo at least the very beginning. So let's go. Um, so I'll present you today my Ph.D. Thesis titled "Devices for Communication with Individuals Who Are Deafblind." And in order to explain well this project, I will divide my presentation into 5 different chapters, and I will start by the standard and classic context and state of the art. Communication is mainly based on visual content and auditive content, but if you are blind, well, thankfully you can still rely on audition such as speech to communicate, but if you are deaf, you can still rely on text, but also sign language to communicate. However, if you are both deaf and blind, communication is much more complicated, and that is the daily life of millions of individuals all around the world. This combination of hearing loss and vision loss is called deafblindness, and the degree of blindness and the degree of deafness induce a lot of variability into the way you can communicate. In order to explain our project, I will just touch the touch-based communication methods, but not the others. So the first method is called Tadoma methods. Basically, the deafblind person puts one hand on the face of the speaker to understand how the interpreter moves the mouth, the nose, the throat when during speech. The second category is the tactile fingerspelling language. It is based on sign languages. So when an interpreter signs, the individuals who are deafblind can put one hand or two hands on top of the hand of the interpreter. The third category is the finger Braille code. It's based on Braille, but instead of having the 6 dots of a Braille cell, each dot is represented by one finger, and if you want to display one cell, then you will have to tap the corresponding finger. The last category is the tactile fingerspelling methods. Basically, you use one hand of the person who is deafblind as an input, and so the interpreter can draw symbols, tactile symbols, on the palm, but also the fingertips. In the other hand, if we look at what is commercially available in the assistive technologies for communication, well, there are only Braille-based devices. So here you can see that there are 2 different worlds. One world where you have the natural way of communication of the deafblind community, and in the other hand, you have devices based on Braille code. So you have these 2 worlds. So our project was to try to create a converter that can convert visual content and auditive content into natural tactile communication techniques. And one way to do it is to emulate the tactile fingerspelling methods. So I will show you a quick video. So you have, so on the right part of the screen, he will receive a tactile symbol on the palm made by an interpreter. This idea of developing such devices is not new. It has been done 12 years ago by Caporoso with the Merci alphabet interface. Basically, it's a glove with several ERM motors, vibrator motors. So it's portable, and the idea was to emulate the Merci alphabet, which is the alphabet, tactile fingerspelling alphabet of Italy. 4 years later, Goldner, Bingley, and Jost developed the mobile long glove. Same idea, ERM motors, a glove, but this one is made for the Lom alphabet, which is the alphabet of Germany. These designs are very simple, very efficient, portable, and affordable. However, it produces stimulation very different than what a human does when one of techniques of tactile finger spelling is used. It has also a constant contact with the skin, as it is a glove, so you have friction and constant pressure all around your skin. And it also, this kind of system also allow mechanical crosstalks between the different part of the design. So the objective of this project was to design and validate a device for tactile communication with individuals who are deafblind. And in order to do that, the device has to take into account several requirements. And the first requirement is, as the two other devices, to be affordable and robust. But this time it has to care about the natural tactile sensations, but also to minimize the constant contact with the hand. In order to be used for a prolonged period of time, the device has to be also comfortable. In order to answer these different criteria, well, we'll have to use off-the-shelf components and embed it into 3D printed components. So it would be in a simple architecture, so everything would be robust but also affordable and easy to make. And in order to recreate this natural tactile sensation, well, we could actually try to develop a robotics hand with 5 fingers in the palm. However, it would be first quite complex to create, and then quite complex to control in order to properly touch the skin of the person who is deafblind at different places. So one good way to do that is to do the same as the two previous researcher groups and create our own actuator array. However, we'll have to care about the way we convey the information. I'll explain that a bit later. To minimize the constant contact with the hand, we could use on-hand device similar to a computer mouse, so it would reduce the area between the hand, in contact between the hand and the device. And for a prolonged use, well, the device will have to care about the shape of the hand. So one good way to do that is to mimic the rest position of the hand. To summarize, in one side, on the left part of the screen, you can see the actuator array. So we have no idea how it will be managed yet, but we have an actuator array that will have to be under the hand of the user, and that has to follow the shape of the hand. So we have this concept of tactile communication device, but we will go from these two ideas we had just before into something a bit more tangible. But before going too much into the detail, I would like to talk about Sven Top and Geraldine Miroy. Sven Top is a person who uses tactile finger spelling techniques of Australia, and he wanted to have a device that fits his needs, and so this is how the project started actually. Geraldine Miroy, she's an interpreter and an expert in tactile finger spelling techniques. So she was there from the beginning as well, and this is how the project started. So we decided to base our approach first on the Auslan tactile finger spelling alphabet, as it is the alphabet used by Sven Top. So how can we extract, reduce, understand this alphabet to know how we can emulate it properly. So actually you can reduce these 26 letters into two main variables, and the first variable is the contact type. So the contact type can be a tap, so you tap the finger, you tap with one finger, for example, on the skin and you release the pressure. It can be a tap and slide, so you do the same, but instead of staying at one location, you move to another location before releasing the pressure. The second variable is the contact size, so it can be of the size of a fingertip, such as the letter D, or it can be larger than the size of a fingertip, such as the letter V. So we have these two variables, and by combining them we can create 4 different groups. And the first biggest group is the tap letters of the size of a fingertip. The second largest group is the tap letters larger than the size of a fingertip. And the third group is the tap and slide letters of the size of a fingertip, and the last group has only the H letter. You touch the skin at the bottom of the palm, and you move forward up to the fingertips. So in our approach, we'll have to care about the group 1 in order to emulate well this group, and then with the features we design from the first group, we will try to understand how we can make the second group and so on. For the first group, how do we recreate a tap of the size of a fingertip? So the question is simple and the answer is simple as well. We need a contactor cap that is of a size, of a shape, and with the same elasticity as a fingertip. And in order to reproduce the tap sensation, we'll need an actuator that is able to have a resist position and then can be activated to touch the skin for a certain amount of time and then release the pressure by being deactivated. For the second group, well, actually we can think of this array of actuator as being a screen. So we can maybe have like 200 actuators under the hand, but it will be extremely difficult to control. So we'll use what is called the 2-point discrimination threshold. So I'm pretty sure everyone experienced that before. So if someone is touched you with 2 fingers on your back, for example, and if you had to guess how many fingers is touching you, well, this is the question. But if you are making the 2-point getting closer and closer, at some point you will not able to feel 2 points, and this is the threshold we are searching for. So in the classic case, they use a compass, so very narrow ends, with a static stimulation. So it's still stimulating your skin until the answer of the user. And it has been found that you can separate 2 points for about 6 millimeter in the palm. And this is the threshold. And in our cases, we have quite a different setup. So we have a round and large contact area, and we are using a dynamic motion as well. So we briefly touch the skin. So we expect that we can space the 2 actuators from about 10 millimeter. So on the right part of the screen, you can see 3 actuators. If we activate them at the same time, we can make the person perceive not 3 discrete points, but if it was just one large and unique contact. For the third group, well, we'll use the phenomenon called haptic apparent motion. So basically, you have 2 actuators placed on your skin. You can see on the left part of the screen. If the actuator A is vibrating, and over time, this vibratory content moves from the actuator A to the actuator B,
well, you will not perceive like if one actuator is activated than the other, but you will feel like there is something moving from the location A to the location B. So we will use this to create our slide motion on the skin. And the first group is made of lines of actuators. So with the 2-point discrimination threshold and the apparent haptic motion. To sum up this section, we need to have an actuator that can do a tap, but also that can vibrate. And we should place actually 24 actuators under the hand in order to reproduce the entire alphabet. So it also induces that the actuator design should be small enough to accommodate this number under the hand. Unfortunately, there is no commercially available actuator with these features, so we just decided to do our own actuator. So the actuator is based on the electromagnetic linear actuator design. So it's made of a moving part that moves vertically and that has magnets, a static part that is surrounded by a coil. So when you activate the coil, actually you make the moving part goes up and goes down if you turn off the current. So we can recreate from that our impact mode. And we can also make the shape of the top of the actuator similar to a fingertip. For the vibratory mode, we can do the same. So gently it goes up to touch the skin, and then by making the current varies inside the coil, you can recreate these vibrations. And we can make it very in a simple way, as it is a linear system, but we can also reduce the size of our design to something small enough to accommodate these 24 numbers under the skin. So it looks like this. You have on the left part of the screen, the moving part. On the right part of the screen, you have the static part. I'll just show you quickly. You have the actuators at the bottom connected to the cap support that is similar to a fingertip. And the static part is made of a 3D printed support for the coil. And everything is connected with an epoxy layer. And at the very bottom, you have 4 little magnets. And these 4 little magnets aims one specific goal, is to cancel the fall of the moving part to avoid the moving part to hit the bottom of the actuators and create noise. So we characterize our actuator with these 2 modes, the impact mode and the vibratory mode. We send a squared signal and we extracted the displacement of the actuator. So it looks like this when you send a squared signal. And we have 5 millimeters of displacement, which is what we need to recreate this resist position into impact into resist position. For the vibratory mode, we send to the coil a swap sign signal from 20 Hertz to 500 Hertz. And we get this response. So you have the x-axis, which is the frequency, and we get the magnitude, and we have a quite flat response up to several hundred Hertz. So it goes up and we can vibrate. So we have our 2 modes of actuation for our actuator, and it's small enough to accommodate 24 actuators under the skin, under the hand. So we made an actuator that is able to create a tap and vibrate also. So the tap should be closer to what an interpreter does when this interpreter signs on the hand, which is, as we said before, quite different than vibrations. So maybe it's more natural to have tap rather than vibrations, but maybe from a perceptual point of view, it gives the same information. So maybe you are as accurate with tap than with vibrations. And it can be a problem as we have a self-made components that cost more than 10 euro compared to ERM motors that are off-the-shelf component and that cost only 2 euros. So we decided to compete these 2 modes of actuation, tap and vibrations, into an experiment. So before going into the experiment we run, I would like to do an experiment right now with you. So it will be a counting task in Vision. So I will display for a short period of time on the screen white dots, and you will have to count them. Okay, let's have a first try. Whoop. So okay, this one has that was two actually. Let's do another one. So this one is maybe a bit more complicated. That was 5 dots at the same time. Let's do another one. Okay, there were 12 dots at the same time. So this experiment in Vision has been done by Mendele and Shibo 40 years ago. So we used a similar process, but instead of having dots, we used tactile input. We used tap and vibrations. So as there is an infinite possibility to simulate the skin, we choose our context, and we decided to focus on the finger Braille to stimulate the skin. So just to, as a reminder, a finger Braille is, instead of having the 6 dots of a cell, well, each dot is represented by a finger. So we made 2 devices. The first device is based on our actuator, the tap actuator. And the second device is made of the ERM motor. So we have our device that create the tap, and we have a specific device that create vibrations. So I will show you briefly how the first device. So basically, you can use one actuator at the same time, 2 actuators at the same time, 3 actuators at the same time. And so that's what we did. And we asked the participant, how many items did you feel? Was the idea. But we also added 2 other variables. So we have our type of stimulation, but we also added 4 different levels of duration. So the duration of the stimulation could be 50 milliseconds, 100, 200 milliseconds, or a continuous stimulation until the answer of the participant. And we coupled these 2 variables with the number of contacts. So 1 actuator activated, 2 actuators activated, and so on, up to 6 actuators activated at the same time. So the question was, how many items did you feel? But we also asked just after that, how confident are you about your answer? And we extracted the 3 main outputs from that. The first one is the error rate. So for each combination of the 3 variables, we extracted a value that represent the error rate from 0 to 100%. And the reaction time, well, the same idea, but in second. And the confidence rating, we also have a confidence rating for each combination of the 3 variables from 0 to 100%. And these are the results. So on the top of the graph, you have 8 different colors that represent the combination of the type and the duration of the stimulation. So the triangles are the tap, and the dots are the vibration type. And darker the color is, longer the stimulation was. And so we display these 8 conditions with the last variable, which is the number of items. So as you can see on the screen, this is the mean error rate for the 21 participants. So if you look at the number of items equal to 1, you can see that people has almost no error. So they are very accurate with just 1 actuation, which is to be expected. But it increased with the number of items. But if you look at the mean, you can see that people tend to be more accurate with tap rather than vibrations. If you look at the reaction time, actually, we display the same way. So 8 colors for the 8 conditions combined with the number of items. There is no real impact of the number of items, neither the duration of the stimulations. for the reaction time, but there is a clear significant impact of the type of the stimulation. So your answer, the participant answered quicker with tap rather than vibrations. The confidence rate. So just be careful. So it's displayed the same way, but the y-axis is inverted. So 100% of confidence is what we have basically at 0 usually. So when the number of items is equal to 1, people tend to be very confident. So we've done this, we use this little trick to be able to impose the confidence with the error rate. So I'll go back quickly to the error rate and then go back to the confidence. So we'll see that people tends to understand if what they think is actually correct or not. But in order to extract better this result, we subtract for each combination the confidence rate by the error rate. And this is the result we have. So we call that discrepancy, and it represents the overconfidence or the underconfidence. So if your result is positive, it means that you are overconfident. So your estimated, actually, your results too much compared to your performance. And you can see that we tend to be overconfident for all the conditions. And but another thing we can see from that graph is people tend to have a better estimation with tap rather than vibrations. So to sum up these results, we have these actuators that create a tap. We can be more confident about it because it's a phenomenologically reasonable contact with the fingers. The response of the participants were faster and more accurate than with vibrations. And the participant had a better estimation of the information. And this fact could lead to fewer interpretation mistakes. So for example, if someone is send a message through this device, if you had vibrations, then maybe you think that what you receive is what you think and you're confident about it. But if it's not actually what has been sent, it can lead to interpretation mistakes. So we developed a concept of our device. We made an actuator specifically designed for that. We assessed that actually tap are more interesting to convey information compared to vibration. So we decided to create this whole hand tactile communication device. Just as a reminder, we wanted to create the Ozen tactile alphabet, fingerspelling alphabet with the device, and we should have this user interface that is that minimizes the contact area, but also allows a prolonged use. So to have to respect the shape of the hand. And this is what we've done first. We extracted the rest position of a hand, and we created a user interface, a shape. From that, I'll show quickly the video. So to give you an idea of the orientation of the shape, if you place your left hand in front of you with your finger pointing on the right side, the palm pointing the floor, this is the orientation of the shape. So the fingers are on the right and the palm on the left part. So this is the hand support, and we actually we wanted to have a device that fits to almost all hands, but it's quite difficult to do because we are all different. So we just asked 21 participants to put their hand on this shape. We place manually at the correct location each actuators for each pictures, each hand, and we average the position of the location of each actuators. So you can see that on the left part of the screen, but on the right part of the screen, you also have this squared. squares that represent the average location for each actuators with a random picture. We face also another issue. When you have two actuators close to each other, well, if you activate one, the other one will be activated at the same time. And this is due to magnetic interaction between the permanent magnets of the moving parts. So to answer to this issue, we just separated the actuators vertically of a distance of 27 millimeter to be able to control them without magnetic interference. So on the left part of the screen, you can see a curved view of the hand and the support of the hand. And on the top, you can see the actuator support. So it's made of 24 towers, and it embeds the 24 actuators. And you can see that the towers are at different heights to avoid the actuators to interact between each other. And it leads us to another thing. We had now a toll road, so we just created a guide to guide correctly the actuators. So the actuator is comprised between two parts, the housing and the guide. And on the top, you have the contactor of the actuator. So we still have in mind to create a device that send clear signal. And to do that, we, as I said during the third part, we created an actuator that has a recessed position. So when we don't need it, it's not creating a constant contact with the skin. In the same way, we developed a hand support that has a minimum contact with the skin. So there are holes for the actuators as access point. And this is one area, a second area, and a third area. And these three areas are made for as a contact with the skin. It allows to minimize the contact, but also allows the rest position of the hand. We also try to minimize the crosstalk between the different components. So to give you an example, if one actuator is touching the skin, and if you place one accelerometer very close to this location, this is a signal you get. And if you place one accelerometer at the bottom of the actuator, well, you can record some noise. And actually, if you touch the bottom of the actuator, you can clearly feel it. So for the purpose of the explanation, I will change the shape of the finger to a box that represents the hand. I will also add the hand support and also the actuator support that comprises the 24 actuators. So if the actuator support is connected to the table, well, you just create a path through from the actuator to the table, which is fine, until you do the same with the hand support. And then you create a path through the bottom of the actuator to the hand, and that create noise. And this is actually what the type of architecture you have with the glove, where the actuators are sharing the same support as the hand. So to avoid that, we place two damper system, and we characterize it by placing one accelerometer on the actuator and another one on the hand support, and the ratio between the two is of a factor of 1,000, which is what we need to avoid the noise to come to the skin. To give you a brief overview of the whole design, well, it's divided into 4 different parts. So you have on top the input. It can be voice recognition, a voice recognition system that will be converting voice into text. And then we have the text as an input of our software. So it's this graph is divided into the software, the electronics of control, and then the actuator. So the software is made of 2 parts. You have the text to tactile converter that has a database of tactile symbols. And when text is sent into this part of the actuators, that is, and it will convert this text into a 3D matrix that corresponds to the behavior of each actuator. And so you have a dimension that is the number of actuators, and the other two are the intensity of the voltage over time. And so you also have, in the other hand, the digital to analog converter driver. So these two parts are separated. So it's two threads. So you can have an input, and at the same time, the software can manage the device. So it transfers this digital signal through SPI to digital to analog converter that will transform the digital signal into analog signal in volt, and it will be sent to an operational amplifier configuration that will be connected to the actuator. So we'll have this op amps configuration for each actuator. Well, this is the overview of the device. So the black box on the table is made of the electronics and the Raspberry Pi, where the software is, and it's connected with these two gray ribbon cable to the device itself. So on the screen, there is, for now, only the actuator support. So in white, you can see the towers connected to the guide interface, and in between the two, you have the actuators. And this part is only connected to the green component with the dampers you can see here. So if you can control the actuators one after another, or at the same time to reproduce the vibrations or the haptic apparent motion. And then you have the user interface, I mean the shape, and the rest position. So you can have this tactile feedback from the actuators. We tried with Sven Top, this device. He had no training on this device. That was the first time for him to use it, and he had no idea about what will be sent. And you can see on the video that Ophelia used a phone. So we use voice recognition, and the phone is connected to the Raspberry Pi on the box that will receive the text, and then the Raspberry Pi will convert the text into the tactile, and then the tactile will display to Sven, and Sven will receive the message with the tactile fingerspelling alphabet. So Ophelia asked Sven how was the cake, because we actually ate a cake for lunch. And so it's time for the device to process it. And so he got it for the first time. That was quite amazing. And his feedback was the symbols were clear and noticeable, however, still different than what a human usually does. And there is a clear lack of flow and prosody during the process. So this blue device was made of the location of the actuators were placed by using 21 hands. So I decided to create a personalized size device for them. So this is what you can see on the screen. So he used the device for several seminars and international conferences for several hours. So this time we used a keyboard instead of a voice recognition system, but it works the same. So you send text to the interface. So the rest position of the hand allows a plunge used, but it's still different than what a human does, and it still needs, there is a need of prosody. So we, as a work in progress, we started to look at the vibratory content that is generated by the device. So we used the accelerometer array developed by Yixian Shao and Yang Zhao, and we extracted from different letters made by the device, but also made by a human, the vibratory content. So to understand if we can make them match or not. And the preliminary results we have is also the confusion matrix on the left part is a similarity between the human-made signs. So you can see that each letters have a very unique signature with the human-made signs, but it's also the same actually with the device-made signs. So there is almost no mistakes between or mismatch between the different letters. But if we compare the device-made signs with the database of the human-made signs, then we can see that there is a clear issue between the two. So the vibratory content made by an interpreter or made by the device is different. So it matched with the perception of Sventop. So that's also interesting to look at this. We can maybe try to make the two vibratory content match. So if the device can reproduce exactly what a human can do, maybe the perception will be the same as well. So just to summarize this section, I'll be brief. I developed a tactile converter that converts audio or text or visual input into tactile output, and specifically the Osland tactile fingerspelling technique. To sum everything up, I've developed an actuator that is specifically designed for tactile communication. I've made an experiment that assess that tap stimulations are more appropriate compared to vibration to convey information, in particular for a counting task. And I developed several versions of a whole hand device for tactile communication, and we are at the beginning of understanding why it's different than human, an interpreter. For further research, I will still want to try to understand this vibratory content aspect, but we can also evaluate as the device with different individuals who are deafblind, because we tried only with Sven. So it would be interesting to see if what we have with Sven is also true with a bigger group. Another thing we can do is to create a guide for the actuator that allows the actuator to be used efficiently in any orientation. As now, it's efficient, it's optimized for the vertical use. And we could also think of creating an experiment based on the tactile apparent motion by using a novel approach. Thank you for your attention. I will try to answer to your question now.
So many thanks, Basil, for this very interesting and clear presentation. So we can now turn to the questions session. So the order will be the following. First, Marie